Hello and welcome back. For the rest of the section, we're talking about quadratic surfaces. Now, technically, a quadratic surface is any surface that follows the general equation, this one. So that's a lot of coefficients, a lot of constants in there. You can see quadratic corresponding to the highest power of x, y, and z, right? Squares in each of them. That's the highest power we can have for any quadratic surface for our variables. And then we also have constants for mixtures of variables, x times y times z, and then each individual separately, and then finally a constant term. Anything that has this form is a quadratic surface. This gives us a very general family, a large family of surfaces, but we're going to focus on sort of three particular families: ellipsoids, paraboloids, and hyperboloids. You might be recognizing this term oids. This is sort of telling us it's like a three-dimensional, there's a clue that it's a three-dimensional version of an ellipse, parabola, and a hyperbola. So why do you think I made those intro videos where we looked at ellipses, parabolas, and hyperbolas? Well, because we're going to have three-dimensional versions of those things. Because we're in three dimensions, there might be, we'll see with like parabolas, paraboloids, there's like two different varieties of these. We'll get to that in a second. In this video, I'm just going to cover ellipsoids. So we're going to start with just an equation of an ellipsoid. Consider the graph of the equation, this one. So one way to recognize an ellipsoid is if I sort of cover up one of these variables, what I get is what looks like an ellipse equation. If I cover up the z, I get an ellipse. If I cover up the y, I get another ellipse equation. If I cover up the x, I also get an ellipse equation, but in terms of y and z. So what that's telling me, that what I'm doing there by covering up one of these is I'm setting z, let me just do it. Let's say set z equal to 0. Then what we'll get is x squared over 4 plus y squared over 16 equal to 1. And that's an ellipse. And this is the xy trace. If I set, let's say, y equal to 0. Oh, and let's actually identify what ellipse this is, right? This is an ellipse. It's going to be in the xy plane. And my x is going to go from 2 to -2. My y is going to go from 4 to -4. So it's that ellipse. Set y equal to 0, I get x squared over 4 plus z squared equal to 1. Again, we have an ellipse. This is going to be the xz trace, so I can draw this, right, in the xz plane. That's actually how I'm going to do this. I'm going to draw each of these three traces, and then we're going to kind of fill in the rest. Here I'll set x equal to 0 for the yz trace. Set x equal to 0, this term vanishes. I get y squared over 16 plus z squared equal to 1. So yeah, for each of these, so here my x is going to go between 2 or -2 and 2. My y will go between -4 and 4. Here my x again goes between -2 and 2. My z here will go between -1 and 1. My let's see, my y here goes between -4 and 4. And my z again goes between -1 and 1. So let's go ahead and draw these traces. I didn't follow my pattern. This is an ellipse, and this was the what? This was the yz trace because we set x equal to 0. So I'm going to draw each of these three ellipses, and then we're going to talk about how to fill in the rest of it. Whoops. Ah. Oh no. Control Z that. All right, back to where it was. Phew. All right. So the xy trace, this is the one that's sort of on the floor in the xy plane. Parabola x from -2 to 2, so I better draw. I'm going to make this a little bit big. 1, 2. There's 2. 1, 2. There's -2. And then what? My y goes between 4 and -4. So I'll go 1, 2, 3, 4. 1, 2, 3, 4. And I'll go ahead and draw my ellipse in the xy plane. I'm going to do this in blue. A student mentioned last time I taught this class that they liked when I drew sort of these perpendicular traces to each other in different colors, so I'm going to try that. And then, okay, let's see. I'm actually going to redraw that. I didn't do that quite in perspective. I I got to remember I'm in 3 dimensions here, so this is going to look a little bit more like that. All right, that's maybe a little bit better. Maybe not, I don't know. So that was the XY trace that we just drew. We drew this ellipse. Let's draw another ellipse. This is the XZ trace. So here is the X. I didn't label these axes, did I? X, Z. So the same labeling we always do. Z and Y. So that's the XY plane we did. Let's do the XZ trace. X again goes between -2 and 2. Now Z goes between 1 and -1. So maybe I'll draw 1 here. And about the same distance down -1 here. So in the XZ plane, we have another ellipse. I'm drawing this again in perspective, though. I'm going to use, let's say, red for this one, for the XZ trace. It's going to come up from -1. There's sort of this front face of the ellipse. Up to 1. Okay, these aren't supposed to intersect. They should actually be intersecting over here. And then I'm not going to see this part of it, and so I'm going to draw dotted lines. And you know what? I should have done that for the XY trace. I'm going to back up. No, I'm not going to back up. That's fine. It's fine. And then let's do the YZ trace. So Y went from -4 to 4, and Z again from -1 to 1. And I am going to see all of this one. This comes up. This is sort of the one that we're flush with, that we're facing. And down like that. So that's the trace in the YZ. And then the rest of the ellipsoid. So here's my X1. Goes around like that. And so what we get is sort of a spherical looking object, but it's not quite spherical because not all of our axes are the same length. Instead, we get what's called an ellipsoid. So because the drawing it's a little bit difficult, let me jump to an interactive figure in our textbook. There is an ellipsoid. So I'll drag it around. There's the figure I was drawing. So we drew this one in the XY plane. We drew one in the XZ plane. Let me actually turn on those traces. So we drew this ellipse. We drew this ellipse. And we drew this ellipse. And then we sort of just kind of connected up the rest of it. Yeah, so this isn't, it's not quite the figure we drew. This is a little bit different of a variety of it. Notice here with this equation, my x is going to go between 3 and -3. My y is going to go between 4 and -4. Those are the extents of the y. Oops. And then my z goes between 5 and -5. So because our z went between 1 and -1, we just had a 1 down here. It was shorter than this one. It would have only come up to here, and that's why they didn't pick it for this interactive figure. It doesn't look as nice. And so maybe I'll jump back to my drawing. Can you picture it a little bit better now? Maybe. I can draw some of these other ones too. Some of these, this will come up to the green, back down to the blue, back down to the blue. I can try and draw some more of those, but hopefully you can sort of get the idea from this. Again, the drawing of it isn't the most important thing. This isn't a drawing class, and when you're in the field and you're in your job and you need to visualize one of these surfaces, and you might have to do that at some point, the key is to be able to recognize what the surface is from the equation. That's what we're trying to get to, not generating a great drawing by hand. We have computers to draw these for us nowadays. It's okay if you can't do this super well by hand, just like I can't do it super well by hand. But I can recover the traces, and I can recognize that this is the equation for an ellipsoid just based on the structure of the equation. So again, key thing here is going from the structure of the equation to what the figure is going to look like. Can you form a mental image of it? And then also being able to do the opposite. If I see a surface like this, do I know what kind of figure it is? Can I recognize it's an ellipsoid? And then can I recover what the equation is going to be? That's really the key here. But this idea of drawing it will help us to do that. So that's why I focus on that. Okay, that's it for this one. In the next one, what are we going to look at? In the next one, we're going to look at paraboloids. Cool. I'll see you there.